So, right. So I'm supposed to try to explain a few things around these ideas. And if you came for the Landau-Ginzburg models, you will be very disappointed, because what mathematicians mean by that is, I think, some kind of completely degenerate version of what physicists care about or something. For us, it just means a space with a function, really. And okay, so anyway, what is the story here? So homological mirror symmetry is what mathematicians have done out of mirror symmetry by trying to put more and more mathematical structure into it. And the version that Kontsevich first formulated in 1994 said essentially, if you have a pair of mirror Calabi-Yau varieties, then there would be an equivalence of categories between, say, the derived category of coherent sheaves of X, and on the other side, something called the Fukaya category of Y, which involves its symplectic geometry. So I think for physicists, these are supposed to be like categories of branes in type A and B topologically twisted string theory, something like that. For a mathematician, so coherent sheaves is, well, on a, say, complex or analytic or algebraic space. That's basically a generalization of holomorphic vector bundles, where you also allow vector bundles that are supported on some subvarieties and whose rank can jump along them. You allow things like kernels or co-kernels of maps between bundles. And derived means that you allow also complexes, bounded complexes of bundles up to homotopy. And that's kind of some algebraic flexibility that lets you, for example, replace a sheaf by a complex of bundles that resolves it. And that's easier to do homological algebra with. So the Fukaya category, it's a category as well, whose objects are Lagrangian submanifolds. Means something of half a dimension. So these are real dimensions. Yes, symplectic geometers are real differential geometers of half a dimension in a symplectic manifold on which the symplectic form vanishes completely. And so, for example, you can just think of Rn inside R2n. That's actually a universal local model, slightly more ambitious. You can take the base or the cotangent fiber in a cotangent bundle. In the context of algebraic geometry, the real part of a complex manifold which has a real involution would also be Lagrangian usually. Okay. So, right. And so the Fukaya category has these things as objects, together with suitable extra information that I don't want to tell you too much about. But you can add things like local systems, formal deformations, and so on. The main thing you're supposed to do with these is intersect them. And maybe I should say something about thinking of what are the morphisms. Oh, yes, I will say now. Okay. Morphisms are given by intersections. Okay, so the morphisms is a vector space over an unspecified field for this talk. You can say complex numbers, but to be more honest, you should have maybe some field of power series, something generated, so with a basis, generated by their intersections. So maybe the important thing to note is, since these are half-dimensional cycles, if you make them transverse, symplectic geometry is very flabby, so you can always perturb them to make them intersect transversely. They will intersect in isolated points, and you call these generators of your Floer complex. Okay, so this is called the Floer complex. But right now it's not that complex, it's just a vector space. It has a grading by some kind of rotation number. Basically, if you see, inside a Riemann surface, arcs or closed curves would be Lagrangians. And then you have a notion of a rotation number as you move from one intersection to another one. And that lets you grade things. And there's a generalization of that in any dimension. But this is not the whole story. You would like this way of measuring. So in some sense, the rank of this measures, of course, how many times L and L prime intersect right now. But you would like this to be more invariant under suitable isotopies. So there's a notion. Okay, so maybe I should say something else. So this carries a differential called the Fleur differential, which counts holomorphic disks. So you choose some complex structure if you don't already have one. In mirror symmetry, you already have one usually. It counts holomorphic disks between intersection points of L and L prime, but whose image looks like this. You look for a holomorphic map from a disk to your manifold with part of the boundary on L, part of it on L prime, and just two corners. And then you will declare that this contributes to, so let's call this point P and Q. This contributes to boundary of P equals some coefficient, some weight, times Q. And then, of course, and so on if there are other such disks. So what does this achieve? So from a topological perspective, if you have two submanifolds in a smooth manifold intersecting in 2 points with a connecting disk like this is sometimes called, if this disk is embedded, this is called a Whitney disk. You can use it to wiggle the submanifolds and cancel the intersections. And somehow it's an old observation going back to Fleur, I think, that in symplectic geometry, if you want to wiggle while remaining Lagrangian, and with this extra condition called Hamiltonian isotopy, which means you do not sweep any area. If I move this up, I have to move this down or something. I cannot sweep non-zero symplectic area. Anyway, so Lagrangian isotopies cancel disks, cancel along holomorphic disks. So the idea of doing this is you achieve invariance under Hamiltonian isotopies of L or of L prime. And so symplectic geometers outside of mirror symmetry care about this because it gives a lower bound on how much L and L prime must keep intersecting, even after arbitrary isotopies, staying, of course, Lagrangian. And the Euler characteristic of this is just the homological intersection number. So you know, of course, the algebraic intersection number gives a lower bound just from pure topology. But there's usually a stronger symplectic bound. And that's what this was invented by Fleur to kind of measure.
So what is invariant is the cohomology of that complex?
That's right. And under suitable assumptions, which often fail. I mean, sorry, so this is invariant under Hamiltonian isotopies. Sorry, so cohomology, which is called the Fleur cohomology of L prime, is the homology of its complex, is invariant under Hamiltonian isotopies. So there's a technical condition, which is if L and L prime separately don't bound holomorphic disks. Counterexample is if I have, say, this and that in the plane, then I can actually move this. Actually, sorry, the presence of disks actually obstructs d squared is not even zero. In an example like this, if you try, you have two of these kind of differential things. You get d of this point equals that point, d of that point equals that point. It's game over. Mm-hmm. Okay. Yes.
Sorry. So the vector space generated by the intersection point is it the degree zero part of this complex? Or
no. Sorry. So each intersection point has a degree which has to do with a rotation number. I'd rather not spend half an hour on trying to define rigorously the degree.
But it's like the weighted components of this vector space. Then.
It's so the weight. I mean, so basically, like for example, in this example, this might be in degree 0. This might be in degree 1 because basically there's been one rotation of a tangent plane to L prime relative to the tangent plane to L as you go from here to here.
I didn't quite get, so the differential is related to counting holomorphic disks. So P is one of the intersections.
So P is an intersection point, so
Yeah.
it's a generator, it's the basis element of this vector space.
Okay, and so the
Q is another intersection, it's also a basis element.
and the things that appear on the right are all the things which bound the disk together on the right of the
So
equation.
basically, so you think of this as a, this kind of disk with a corner at P, a corner at Q. There's a convention, like, you jump from L to L prime back to L. This is the input, this is the output.
Okay.
This is called the Floer trajectory from P to Q. And then the differential counts Floer trajectories.
And so the dots, would it be, for example, from P to
Like
the other
to
point?
this guy, yes, to prime maybe, yeah. Yes.
And the weight
Yes,
is
and the weight
is the
is
area.
to that. So one thing you might do here is have a formal variable T times to the area, exactly, something like that.
And counting these disks, I guess they're probably not discrete, and so it's
So you are so in the expected dimension of the space of such disks is the difference in grading, -1 because there's a reparametrization of the domain. There's an automorphism of the domain disk fixing two marked points. So when the degree difference is 1, is exactly when you expect finitely many counts, and so you should say counts index 1.
Index is the Maslov index.
Yes, this is the Maslov index. Sorry, I'm trying to not. Maybe actually I should say the names because that's good for culture. I'm trying to hide the technical things. But, yes, so this is all about Maslov index, and the grading is related to Maslov index. So maybe a small comment, since we are getting into a digression on this, is if I have just a Lagrangian L and a small perturbation of it. You know maybe that a universal model for a neighborhood, there's Weinstein's neighborhood theorem, says that a neighborhood of L always looks like the cotangent bundle of L with its canonical symplectic form. So a nearby Lagrangian is going to be the graph of a closed one form. And if it's a Hamiltonian isotopy, is when that one form is exact. So a common case is to look at L prime being the graph of the F, where F is a function on L. And if it's a Morse function, then they intersect transversely at a critical point of F. And then this grading on Floer theory is the same as the Morse index, because that has to do with the rotation numbers of tangent planes between these intersections. And the trajectories you see inside this neighborhood of L are exactly small thickenings of gradient flow lines of F. And so that means the local Floer theory for a Lagrangian and the small Hamiltonian push-off of it reduces to Morse homology, hence classical homology. Globally, of course, and for two completely different Lagrangians, it may be very different. For curves on a closed Riemann surface, this usually reduces to the geometric intersection number, the smallest intersection number you can achieve by isotopies.
In general, you have your intersection, which would be a -1 sheaves symplectic, and those the homological Thomas invariants and converters work.
There's nothing algebraic. These are real submanifolds.
Okay, so yes,
So I think the simplest thing to say is after a small Hamiltonian perturbation, they will always intersect transversely. If you want, you could actually have them intersect cleanly along submanifolds, and then you can take the contribution to be the cohomology of that intersection locus. So here, each point contributes the cohomology of a point.
Okay. This is because you are in symplectic geometry and I can do that.
That's right. I mean, this is not holomorphic symplectic. This is real symplectic. Okay. So, all right. And okay, so that's the morphisms. Compositions. We need to compose morphisms. And composition of morphisms. So if I have three Lagrangians, it's called maybe L0, L1, and L2. Well, this is maybe what, a generator, sorry, a morphism from L0 to L1 is a linear combination of intersection points between them. Right? So maybe P is a morphism from L0 to L1. Q might be a morphism from L1 to L2. Let's think of R here as a morphism from L0 to L2. I can now ask about holomorphic disks. which look like that now. So holomorphic maps from a disk with 3 marked points, with boundaries going to L0, L1, L2, and the marked points going to P, Q, and R. And so basically, like the composition of morphisms counts. So now index 0, so that the dimension is 0. So things that come in 0-dimensional families, disks of this kind. And so now what you would see in this case is that, for example, P composed with Q, P composition is usually written this way, is, again, so T to the area of this disk or something like that times R. Okay. So in some sense, you could say this is an intersection theory, but where instead of, in usual, say, cohomology, the way you multiply, the way you make cohomology of ring is by classical intersection products. Sorry, this doesn't quite make sense as an analogy. I was going to say, instead of looking for triple intersections, which wouldn't exist, you deform them by holomorphic disks, and that's what gives you compositions.
You identify both the intersection points as basis elements and as morphisms?
Well, I mean, once it's a basis element of a space of morphisms, it's an example of a morphism. Right? A morphism is a linear combination of intersection points.
Yes, okay, no, it's fine. It's okay.
Sorry. Maybe my coefficient field, which I guess seems to be defined to be maybe a power series in some variable T.
And so how does composition behave with respect to the grading?
It's additive, it's graded. Okay, so because this index is like, this works exactly when the degree of R is equal to the sum of grades of P and Q. Okay, but since we're getting excited about degrees, I should kind of, everything fails in this world unless it doesn't fail. To have a grading, you need the Calabi-Yau condition, which is good. So I would say this is Z grading requirement. I'm not dependent for the second. Okay. Basically, if you just think of Riemann surfaces, on a torus, you have a global trivialization of a tangent bundle that lets you talk about rotation numbers of curves drawn on a torus intrinsically. On something of genus not equal to 1, well, if you look at the equator on the sphere, does it go clockwise or counterclockwise? That depends on which side you look at it from and so on. So grading is only mod twice the divisibility of C1. Anyway, that's too much detail. Okay, so the other thing I wanted to say is, in a sense, right, coherent sheaves are also some kind of intersection theory for algebraic cycles. Just usually you think more of the holomorphic bundles part of that or whatever. But if I take, say, structure sheaves of 2 algebraic subvarieties that intersect transversely or cleanly along something, then the morphisms between these coherent sheaves will in fact be supported, of course, on the intersection locus. And if you calculate, derived category kind of includes not just harms, but also these X groups. So basically higher cohomologies, higher Darboux cohomologies, say, of coherent sheaves. And so then you end up calculating the Darboux cohomology of the intersection locus as the morphism space. And so, the two pictures are a little bit more similar than you might think at first. But of course, there's no, composition here is really, in this world, it would be just about triple intersections. It wouldn't be about counting some things that have extent. I think string theorists say that in the A model, somehow the classical limit or something like that still has instant corrections, but in the B model, the maps are constant or something. So I'm probably saying things wrong. Okay. All right. So next cultural point I want to do to motivate this LG models thing. Actually, since I'm probably not going to get to anything new or anything, so optional digressions. I don't know. Maybe if people want to see more about mirror symmetry, I can try to do a quick derivation of how it works for elliptic curves, just to kind of convince you that this is a real thing. Okay. So let's say that I'm going to study homological mirror symmetry on a two-dimensional torus. And I want to understand what that might entail. So since I'm a symplectic geometer, I will start, well, I will do both sides at once. Okay, so on this side, I will have the complex thing. So this might be an elliptic curve, which is like a quotient of complex plane by a lattice, but I prefer multiplicative notation. So just by taking the exponential of 2 pi I times these things, this is C star mod powers of some parameter Q, something like that. Okay. And so on that, I can consider various line bundles as examples of coherent sheaves. The structure sheaf is just like the trivial vector bundle. Okay? And then let's call L to be a certain degree one line bundle. Since I didn't really plan for this, I'm not going to tell you which one yet, but you will see what transformation role this has. There's a well-known fact, follows from Riemann or something, that there is one holomorphic section up to scaling of every degree one line bundle. It defines basically a unique point where its sections vanishes. And the most classical example of something like that is the classical theta function, which I will write in this shape as sum over all integers of q to the squared over 2 times z to the n. I hope it's something like that. This is like the Riemann and Jacobi theta functions in some shape. And so this is not periodic under multiplication by under q, z equals to q times c, but there's like a nice transformation rule where you factor in the extra q to the n into a q to the n plus 1 squared over 2, and you shift the sum by 1, and it kind of rewrites itself nicely. So now I can.
This theta function vanishes on the point.
It has 1, 0 somewhere. Which point it is? I think it's probably at q to the 1/2 or minus q to the 1/2, something like that. Yeah, it's not obvious, but I think if you put q to the 1/2, then there's some cancellation between pairs of terms, like maybe for n and 1 minus n or something like that. Just it has to vanish somewhere just from like degree of a line bundle and so on. Okay, so now, so I wrote this formula, but you're not supposed to know it, right? Intrinsically, the category just knows, oh, well, there's one section of this. It's a one-dimensional space of sections. What do we mean when we write a formula like that? That means we're evaluating our section at a point. How do we do that in the category? Well, we take the skyscraper sheaf of a point. And this has one morphism, which I will call the evaluation. And this composition is, because when I say evaluation, to make this a number, I need to choose a trivialization of my bundle at the given point, which is exactly what I'm doing when I write this kind of formula. And then this composition, so from here to here, there's also something I will call evaluation as well now of a function at a point. And the composition of these morphisms gives me, well, there's a structure constant, right? The product of this and that is a multiple of that. Which multiple? It's this quantity. So we should be able to transpose this in symplectic geometry and the Fukaya category of a mirror, which, as I've drawn, is also a torus. Okay, so what do? I will draw Lagrangians from 0. So Lagrangian now is just a closed curve. That's convenient. Maybe I shouldn't be trying to draw this here, but okay. So at some point it comes back. Anyway, it's I'm going to kind of draw in a way that's more convenient. Open this, I think there is a square with the opposite sides identified. L0 is this, L1 is the diagonal line that goes downward. In general, a line bundle of degree k, I would do a line of slope minus k. there's a correspondence between degree and rank and homological classes of curves there that kind of follows from the ethos of mirror symmetry. And then the point will be the vertical line. And so now I have to ask, okay, what are the intersections between these Lagrangians? Well, that's easy. Okay, each intersect each other in one point. So I can treat those as morphisms from L0 to L1 to LP. I will call this one, I don't know, S for section. I will call this one E1 maybe for evaluation on L1, E0 for evaluation on E0. And now I have to ask, S times E1 equals what multiple of E0? What is its number?
So in that case, the objects are just Lagrangians, they are not complexes of
Sorry, so yeah, actually, well, you start with Lagrangians, and then if needed, you enlarge to complexes of Lagrangians. In the, well, there's like work of, I think, Atiyah or something on the classification of coherent sheaves on elliptic curves that tells you there also you can take some shortcuts. Complexes of coherent sheaves you can often kind of replace by some, you can think of them as being basically the derived category is triangulated, and so you can often replace a complex by an honest sheaf, and vice versa. You can resolve a sheaf by a complex, and the same happens with Lagrangians. Of course, the meaning is kind of more confusing and complicated, but essentially the mapping tone of an intersection point you should think of as try to do some kind of topological surgery, connect some operation at that intersection point. Okay. But yeah, here I'm just comparing some sheaves with some Lagrangians. In general, yeah, I should have said, so like the statement I had, you probably want to take some enlargement of the Fukaya category so that complexes are also allowed in there.
But the object that you consider is the entire three-term complex.
Oh, no, I'm considering three different objects here.
Okay.
I'm considering three objects, their morphisms and their composition. I'm just going to give you the mirror counterpart to that. And of course, the statement of homological mirror symmetry is I could take, any triple of coherent sheaves on this elliptic curve. I would find some triple of Lagrangians, or if I'm very unlucky, I would have to take some formal enlargements. And I would be able to compare kind of composition laws on both sides. Okay. So, but what I wanted to do is kind of make the theta function appear, because this is the time when you start believing in this counting of triangles, basically. And okay, so this we say should be counting holomorphic triangles, holomorphic maps from a disk into this with corners at these 3 points. And so you see one beautiful triangle here. Okay, what is the area of this thing? Well, let's call this, there's a parameter here about the position of this point. Let's call that x or something. And then this has area basically x squared over 2, if I think of it as a square thing and so on. So say t to the x squared over 2. Okay. But then there's more triangles, because if you lift this to the universal cover, it will be apparent. Right? That, for example, there's another triangle that goes over here. And in fact, there's more that go around until the next time that you go around to here and so on. So there's in fact an infinite sequence of such triangles of side length x plus n. So it's the sum of n of x plus n squared over 2. And I can rewrite this as okay, so there's a prefactor that comes from like choices of trivialization. So it would be x squared over 2 times sum for n in z of p to the n squared over 2. I see my q here, times t to the nx, which, so that's a really bad case of notation, but you should think of that as, let's change that to z to the n, where z is t to the x. Okay. And you can see I'm really bad at choosing my letters to be suggestive. But so basically, and that factor is just like that. The usual trivialization in which we write the theta function is not the same as the basis given by intersection points. It's a change of basis on these vector spaces. Okay, and so basically mirror symmetry for the torus says that you can repeat this with different triples of curves corresponding to calculations with other kinds of different degree line bundles or vector bundles or product formulas for beta functions and so on. And so there's a paper by Polishchuk and Laszlo from 1998 that does this very explicitly by brute force calculation, basically, for all possible triples of objects. Okay, and
are there other examples where it can be made so explicit?
So explicit, not really. So what you do after that is you realize, wait, I'm wasting my time calculating with so many things because these are triangulated categories. There are mapping codes. And so I just need to understand this very carefully for generating objects. So for example, here, if I just have, say, the O and the skyscraper sheaf, or O and L, eventually I'll be able, by taking bigger and bigger complexes built out of those and direct summands in those complexes to build every possible thing. You see, for example, by twisting O by O sub P, I can produce the line bundle O of P of degree 1. Then I can produce O of 2P, 3P, and so on. And eventually these bundles are ample, which means they have sections which vanish at any point you want. And so from there, you can build all other line bundles and then vector bundles and so on. Okay, and so similarly in the Fukaya category, if you take L0 and LP and you start doing like these connect sum operations, and then you put another copy of LP and you do another connect sum and so on, eventually you'll be able to produce any curve you want by iteratedly doing this. Yes?
If I recall correctly, Polishchuk did this assuming tau is purely imaginary.
That's right, yes.
And has it been generalized for arbitrary choices of B field?
Yes, so essentially one way to say it is the calculation is the same. You just put, you need to understand what's the contribution of a B field to the weights of holomorphic disks, and the calculation just extends, because you could say this is an analytic continuation of the Kähler parameter from the real axis to the complex plane or something. It's really a formal thing. But actually, mathematicians are unable in general to prove that these things converge over complex numbers. So the actual tendency in the field has been the other way around, to keep this T as a formal variable, and I mean, have better notation than me, and have mirrors that are not actually complex manifolds, but rather basically formal schemes defined over fields of power series or things like that. So the mirrors are usually constructed first as things like rigid analytic spaces over a field of power series. And then there's sometimes convergence theorems that say, yeah, but this thing actually exists as a projective variety. We know what it is. So I think physicists would say that's basically because mirror symmetry is only really known to hold as a perturbative phenomenon near what's called the large complex structure limit here and the large volume limit on the symplectic side.
Correctly, Polishchuk Zaslow, when considering some modularized product, like massive products,
yes,
more
yes,
than just 3.
That's right, because to really prove that you have equivalences of, say, of triangulated categories or of A infinity categories, you need to consider slightly more than the calculations in cohomology that I'm showing you. And so there's one more thing to be checked. Basically, there's two different kinds of possible, I would say, enhanced categories, either DG categories or A infinity categories or things like that, that could give rise to these calculations, and you need to know which one of the two it is. So, since we're on that topic, massive products in the Fukaya category come from counting not just like bigons and triangles, but polygons with more sides. They give rise to what's called an A infinity structure in the Fukaya category. And really, you're supposed to have an equivalence of A infinity categories between.
And there's a notion of A infinity category for any on the complex side on the current sheet.
So actually, it happens to be a DG category. You work at the chain level, so with, like, say, check complexes or something, or resolutions, and instead of passing to cohomology, you kind of work with, you get a differential graded category. And the symplectic side somehow doesn't want to be quite differential graded, because at chain level, the product is not associative, and that's why you have these infinity things. There's like formalism that tells you that really this is kind of, at a large level, this is kind of a shell game, in that every infinity category is equivalent to a DG category and vice versa. So I think, yes, on the surface, things look different, but one shouldn't really focus on that. All right. So back to something else. Right, and sorry, so other examples. Now, once you know that you don't need to look at every single Lagrangian, but you can look at a few of them, there's been work on higher dimensional tori by Kontsevich, Soibelman, followed by Fukaya, followed by Abouzaid and Smith, I think. Seidel has a couple of papers. First one was like a monster paper about the quartic K-free surface, and it's like 120 pages of calculations. But then, I mean, the reference you should look at instead is Nick Sheridan's thesis. So Nick Sheridan, was a student of Seidel around 2010, 12, something, about 10 years ago. His thesis was using ideas of Seidel to calculate efficiently what happens for the Fukaya category of a Calabi-Yau-Fermat hypersurface in projective space in any dimension. So for example, the quintic threefold, but you can do all these Fermat hypersurfaces. And the idea is to choose very cleverly one actually immersed Lagrangian sphere in some quotient whose lifts under the covering map will generate the Fukaya category, and that's like a uniform calculation. So that's basically the first, I would say, modern reference in the Calabi-Yau world. And I think he has a follow-up paper, maybe with Ivan Smith, that kind of does it for other examples of Butler-Borisov mirror pairs or something like that.
So there's one single Lagrangian which then generates.
No. So like the Calabi-Yau, say the quintic threefold, if you just take the Fermat quintic, you can project down to CP3 by taking the fifth powers of every coordinate. And the claim is that the weird immersed Lagrangian in CP3, whose 5 to the something 5 cubed, maybe 5, anyway, 5 to the something lifts under this projection map generates the Fukaya category of a quintic.
But so this is then homological mirror symmetry is proved then for the quintic?
Yes. And that's in the Sheridan's paper as well.
Does it apply that the derived category is also generated by the dual object?
Yeah. So surrounding all that, there's been work on generation criteria for categories and so on. And so, yes. Anyway, it's. I
mean, you don't have an exceptional collection for the complex. So.
No, but you don't need an exceptional collection. What do you need? For example, on any projective variety, powers of an ample line bundle will generate. That's a result of, I think, Bondal and Orloff. And that's basically because powers of an ample bundle will give you an embedding into projective space. On the projective space, you have a Bailinson resolution of the diagonal by, O to O of n on one side and exterior powers of a tangent on the other. And then you can pull back that resolution of the diagonal of Pn by the embedding, I think, to get one on. So basically, as soon as you have a projective embedding, you get that the restrictions, the pullbacks by the embedding of the generators for Pn generate for the subvariety. I think. Sorry, I might be wrong, but I think that's correct.
That you need a generating object, but you don't need for it to be a tilting, so to have some constraint on the.
No. And so you choose your favorite generating objects, you kind of match them, you prove that they generate, you prove that the infinity algebras of their endomorphisms match, and that's it. You have a proof of homological mirror symmetry. Okay. So what I was going to tell you about today, and I will still tell you some of it, was actually not in the world of Calabi-Yaus, because there's more to life than that. And so maybe I should say, where did Calabi-Yaus really come up? I mean, okay, from a physics perspective, there are many good reasons for that. But from the perspective of a symplectic geometer, the reason is actually very, very apparent. If you look at, right, so if you look at coherent sheaves on X, you have Serre duality. Maybe I should start on a new board instead of just. I have this tendency to kind of fill in the board at random. At some point, I was a student at ANS, I took aggregation, I had beautiful board work, and then I did my PhD work under Gromov, and then that kind of completely avoided. Okay, so anyway, all right. So the observation is there's one thing that all Fukaya categories of compact manifolds have in common, which is that they are Calabi-Yau categories. So what do I mean by that? Well, it's kind of a completely silly thing, but if I have two Lagrangians L, L1, well, the Floer complex of L0, L1, and the Floer complex of L1, L0, well, they're generated by respectively intersection points of L0 with L1 or L1 with L0. There's not much of a difference. Okay. Now, if you look at the grading conventions and so on, then the grading gets reversed. And if you look at what this holomorphic disk does, is it a trajectory from P to Q or from Q to P that also gets reversed. So in fact, those two complexes are dual to each other up to dimension minus something. So this is a form of like Poincare duality in Lagrangian Floer homology for compact Lagrangians. So in a compact symplectic manifold, this will always hold. And under mirror symmetry, this corresponds to the fact duality. Wait, so I should probably have checked which is which. I'm going to put the canonical bundle here, but I think I might have it backwards. Anyway, something like that. Cell duality has, I'm going to put a plus minus, not catch my bets. And so cell duality says something like that. Now, when you compare the two statements here, you see that basically you have to have a Calabi-Yau because the canonical bundle has to be trivial. So that's great if you love Calabi-Yaus. That's disappointing otherwise. And somehow over time, I think already starting from early mathematical work of Geventhal and on physics side by Auroux and Vafa, it's been realized that there are versions of mirror symmetry for non-Calabi-Yaus. Just the mirror is what's sometimes called the Landau-Ginzburg model, which means the mirror space is not just a space, but it's equipped with a function called superpotential. So basically, there's a souped-up version of mirror symmetry where X is not necessarily Calabi-Yau, and then the mirror is going to be, I will write it complex numbers or something like that.
X should be Fano at least? Or,
So the conventional setup where this works is you need X to have an effective anticanonical divisor. D in X representing the first term. So Fano, for example, helps you achieve this, but there's a few borderline cases where this still works.
Does it imply that X is rigid?
So X is?
Does X have to be rigid?
No. In particular, this might include, for example, elliptic fibrations, rational elliptic surfaces, like including some non-rigid blowups of CP2, for example, things like that. But in fact, so what's even more, and so maybe I should actually deviate the talk to kind of go in that direction rather than the other one. You can actually remove that assumption completely as long as you're willing to have Y be higher dimensional. So maybe I will go into stabilization at some point, but let's start with this. So you could say, for example, okay. So how do we produce these things? So the construction of such, and I think this probably was known to Auroux and Vafa and other people. The list of names on the math side is kind of even too long to really. And so there's versions of mirror symmetry in the closed string sector, like about quantum cohomology or usual cohomology, and there's a version of that for that. But I want to go to homological mirror symmetry. So one cultural thing I forgot to mention. Once you have homological mirror symmetry, it's known you will also recover, say, mirror symmetry at the level of Hodge structures and Gromov-Witten invariants by taking the Hochschild cohomologies of the categories on both sides with suitable structures on them. The words are kind of too much to make sense, and the details are kind of unwieldy, but just for culture, it's known by now that if you have homological mirror symmetry, you can go back to the enumerative mirror symmetry out of it. That's what. So Calderaro and two have done that in part, but I think that was also trying to look at higher genus things maybe. The most commonly considered reliable reference is Gannett, Perrault, Sheridan. So maybe that's not exactly right. That's recovering Gromov-Witten from Fukaya category, but not really getting all the way to the isomorphisms of Hodge structures. So these ones are like about getting not just the most of these Gromov-Witten invariants, but really getting the variations of Hodge structures on quantum cohomology versus cohomology of the mirror.
Does it have a geometric interpretation, just like the triple intersections are now allowed to happen via open string insertons via disks? You now include also holomorphic spheres that connect?
Essentially, yes. So I mean, at least there's a connecting map. There's connecting maps. So let's think about that. Between the Hochschild homology of the Fukaya category to quantum cohomology to Hochschild cohomology of the Fukaya category. Called open, closed, and closed open maps. And what these maps do is basically they consider, exactly. So, okay, what are things in Hochschild's theories? They are basically, they involve, tensor products of morphism spaces in a category. So that involves composable sequences of intersection points. So a Hochschild cycle thing might be a collection of Lagrangians, 1, 2, and so on to Lk, so 0, with intersections, the tensor product of intersection points between them. And so the way you can map this to cohomology is basically, so what the open-closed map does is it looks for, given a tuple of intersection points, you look for holomorphic disks with an extra interior mark point. And you ask what cycle does that interior mark point trace? And you can check that it maps, if this is a Hochschild cycle, then it goes to actually a cycle in the topological sense. So right now there's no ring structure here, so I can't do that. Closed open goes backwards. I have as input this and a bunch of intersections, and the output would be the last intersection. And now these things have ring structures, and you can check it's a ring map by playing games with when you have two insertions. You compare the product structures by kind of taking pictures like that, and you draw pictures about like a disk with boundary mark points and two interior mark points. And what happens when the interior mark points either move away and it breaks into something like that, which is the Hochschild product, or if they come together, then instead you develop a holomorphic sphere, and that's the quantum product. Anyway, there's lots of nice arguments like that. And
this is all genus 0?
This is all in genus 0, yes. Sorry, there's nothing higher genus in what I'm telling you.
But homological mirror symmetry in principle knows about higher genus as well?
We don't have, I don't think we have the higher genus mathematical theory of the higher genus analog of what's the higher genus part of coherent sheaves or something. Right. I mean, even for the closed sector, like, there's all these recipes based on like topological recursion or things like that to associate higher genus B model invariants. I think mathematicians are kind of still slightly uncomfortable about what exactly is the higher genus B model. Anyway, okay. Sorry, so
that's a question.
Okay, so yes, so what's an example of mirror symmetry now in the final world? So the very smallest example is if I look at mirror symmetry for on one side S2, or if you want CP1, maybe I should say CP1 because this is going to be my complex side. And then on the mirror side, I'm supposed to have C star with the function Z plus some constant over Z. Okay. So what am I supposed to do to this function? I'm essentially supposed to study its singularities or something like that. And so one way to visualize this, okay, C star is a cylinder. The fibers of this map are pairs of points, so I need to picture it as something like this. Okay. Over the complex. And so there's two sides to mirror symmetry. There's one that relates the Fukaya category of CP1 to some matrix factorizations of this potential. That's not the side I want to talk about. The other side compares coherent sheaves on CP1 with some Fukaya category of this Landau-Ginzburg model. And so this is where we get into what we want to talk about. So the question is, what is the Fukaya category of the Landau-Ginzburg model built of? Okay, and the answer is its objects are unsurprisingly Lagrangian submanifolds in Y. Okay. But now, okay, so in the compact manifold, we were just going to look at closed Lagrangian submanifolds. Now they're possibly non-compact. But then you want to require that basically the superpotential, this function W, goes to say plus infinity on the ends of L. Okay. To be more precise, I'm going to ask that outside of a compact set, the projection of L looks like maybe a union of, one is the simplest case, but it could be several arcs that go to infinity in the eastward direction. Okay, so in this example, what are the two most basic Lagrangians I can pick? So here are two branch points, like two critical values of its map, which are at Z equals plus minus Q to the 1/2, and this is plus minus Q to the 1/2. And for example, there is an arc here, which is actually R plus in C star, it's called that L0, which projects to this arc. It's the left of this arc under the double cover. And then this is L0. Here is L1. L1 does the same thing, but for the other critical value. And of course, you could keep building more. Like L2 could be something that goes here that twists more around. There are also compact Lagrangians. Like for example, the left of this, which is this Lagrangian.
What do you insist that they all go in the same direction at infinity?
But I insist they all go to the, so I could say they all go to the same direction at infinity, or I could say there's a forbidden direction, which is a ring minus infinity, where none of them go. I don't really care whether they go exactly in the same direction, or if they go in a range of directions, but the basic rule is there's a forbidden sector. Okay. I think from like first principle, so the thing is, this is like a weird math reformulation of what started out as, like for example, some quantities that show up in Geventhal's work and so on are these oscillating integrals of e to the minus w on cycles. And for the integral of e to the minus w to converge on a cycle, you need w to start having increasing real parts so that e to the minus w goes to 0. On that side, the integrals would diverge. And so then you can choose your favorite way of doing geometry around that, but it's basically that. Okay. So now the next thing I need to tell you is, okay, I have my objects, morphisms. So morphisms will again be intersections. But remember, I wanted to do my intersection theory in a way that's kind of more or less invariant under wiggling things. And well, non-compact submanifolds in non-compact manifolds don't have a good intersection theory until you make them have one. And so the rule here, okay, so there's several things you could do. So the first thing you could do is just say, well, I'm going to push my Lagrangians by large isotopies, or I'm going to push them by small isotopies. Maybe for simplicity, I'll just talk about the one that's actually relevant here. So what I will do is I will, before I intersect L0 with L1, I will modify my preferred directions at infinity to make sure that L0 is always counterclockwise from L1. So from L0, L1 will be the Floer complex of what I will call maybe L0 plus L1. And so what I do here is push of until the ends, basically the arguments of W on, well, whatever, until the ends of this projection under W are counterclockwise from those of L1. So that means to calculate the humps between L0 and L1, I should bend L0 up. And then I will see an intersection down here. Now, of course, this is just the complex plane to which everybody projects. To see actual intersections between my Lagrangians, I should look in the fiber over here. What I will do is I will push this up, push that up, and in fact, I have two intersections. In this case, it's the whole fiber. And the geometry of 2 points as a symplectic manifold is kind of very simple. Okay. So in this case, hum L0, L1 looks like it's rank 2. But if I do hum L1, L0 instead, well, then I should push L1 up relative to L0, and then of course we'll project to completely disjoint arcs, so there's no intersections. Okay. And that's it, we've broken the symmetry. So what this corresponds to, this is really the same as the mirror to O and O of 1 on CP1. And when I say hum, I mean hum and next altogether, but this is really hum. Okay. All right.
Excluding a direction, is it equivalent to singling out a window category?
I don't think so. I think this is really no, because this is not in the world of stability conditions. I mean, stability condition would have more to do with, I would say, well, I'm not sure that I understand the answer to that. Anyway, I think the short answer is no, it's just not that. Maybe another thing to say is, in some sense, you know, there's a, I think if you follow the physics, you don't end up at this kind of geometry. You instead end up with a story where you're supposed to look just at the critical locus of W, which would be these 2 points. But you're supposed to intersect them through gradient flow of W, or rather of some suitable phase times W. So what you're doing here, these two intersections, you should think of them, in fact, as gradient flow lines of a potential between these two critical points. And so, you know, this flow line and that flow line kind of just got moved out towards infinity by our kind of device for reducing this to more familiar Fukaya categories. Anyway, yeah, sorry. Yes?
In your power series from the intersections, do you get an additional parameter now taking into account physically the scale of the energy scale?
I mean, basically, the energy scale was just. I mean, so I'm not sure that I know what the energy scale is in the Landau-Ginzburg model context. I would again use symplectic area, basically, or some rescaled version of symplectic area for this. So, right.
The higher ONs would, how would they?
Oh yes, yes.
Lagrangian.
So the higher ONs, they would look like this would be O of 2, O of 3, and so on. Okay. But in fact, now what you realize that, you know, your condition is really at infinity on these things here. An easier picture to draw is to say, okay, this is a cylinder, and just my preferred part of infinity, there's like one arc here and one arc there. This is like near maybe +0, and this is plus infinity on C star. And now I can see, L0 goes here, L1 goes there. But in general, O of K, we kind of go K times around the cylinder.
So it's factored by exponential of W?
No, just by the Z coordinate, log Z or whatever. Anyway, sorry, this is just, I'm just drawing C star by itself. Okay, and this is the fiber towards plus infinity. Access to those 2 points. But yeah, so basically it looks like that, and then it twists a certain number of times around before going back out to infinity. And so, in fact, you have a version of mirror symmetry for toric varieties that looks a bit like that. If you have a toric variety, the mirror ends up being a C star to the n with some Laurent polynomial. And basically, you can build mirrors of line bundles as kind of things that differ from, the real positive part will be the mirror of O, and then you just bend them around as it goes over the moment polytope, basically, to kind of produce mirrors to other line bundles.
And is there a Hochschild cohomology version of this that somewhat connects to the number set?
So I think so, but you have to be a bit more careful now. This category is not Calabi-Yau. And so the Hochschild homology and cohomology of this version of Fukaya category are not isomorphic to each other. And so you have to ask, and that's normal because they're supposed to correspond to the Hochschild homology and cohomology of the derived category of the mirror, which are no longer isomorphic. One of them is the cohomology, is the Durham cohomology, and the other one is the cohomology of the polyvector fields instead. And so these are not isomorphic anymore when you're not on a Calabi-Yau. And so then what you put in the closed sector is kind of less clear. Seidel has various papers on that. Basically, it's like some fixed point Fleur homology of some symplectomorphism of this space that kind of rotates infinity once around. So there are versions of that, but what you put in the anyway, how this comes together is a little bit less obvious. Maybe for what's most easiest to think of, the zero Hochschild homology of this is in the case where you have isolated critical points like this. It's just generated by the identities of the objects, because you have, one thing I should have pointed out, when you have what's called a left-edge fibration, so this is like something with isolated non-degenerate critical points, this Fukaya category is known, has been studied extensively by Seidel, and it's known that it's generated by these kinds of objects. Like you can just take a collection of arcs connecting all the critical values to infinity over paths. I should redo that in a different picture. So if critical points of the body were isolated non-degenerate, and some extra properness condition. But anyway, so then the picture you have in higher dimensions is you have critical values, and over each critical value you will have a singular fiber with an ordinary double point singularity. So there's one singular point, there's an isolated singularity, and there's a preferred Lagrangian that comes out of it over any given arc. And that will be in general a Lagrangian disk, and its boundary at infinity is a Lagrangian sphere, which is basically what's called the vanishing cycle for the degeneration of a smooth fiber to this nodal fiber. Okay, so the picture there was kind of a very degenerate thing of 2 points colliding to a single double point. And yes, it's actually collapsing a zero-dimensional Lagrangian sphere in a zero-dimensional symplectic manifold. But in the next dimension, we might have here a Riemann surface. And what happens is some loop on it squishes to a point to produce a nodal singularity. And this continues on and on. So now these objects, if you choose a collection of arcs like that down there, these form a generating exceptional collection.
The left-edge symbols for this.
Yes, the left-edge symbols. So these are called left-edge symbols. And left-edge symbols form a generating one collection of left-edge symbols for like any system of arcs you choose. And disjoint arcs, one for each critical value. parametric collection. So in here, like the same argument I explained, there's only morphisms forwards and never backwards. And each of these objects is exceptional because if you push it out a bit, there's only one intersection at the tip. So hom2 itself is rank 1, just identity basically. And there are homs forwards, but not backwards. So there you can already get to a bunch of like Fano mirror symmetry out of this setup. But cases that are sometimes more interesting is when you're not a Lefschetz fibration. And then of course the structure of this category is kind of harder to tease out. Since I need to get to a closing point, let me try to actually get to something. So I said, in general, we have this construction produces a mirror value. And the other thing you should know is that the fiber, the generic fiber F of the value, is in general going to be mirror to the divisor D that we chose.
Log Calabi-Yau case.
Yes, so this is in this log Calabi-Yau case, exactly. And so it's very, very silly example. In one, I actually secretly had 2 points as my anticanonical divisor, and the fiber is indeed the 2 points that are mirrored to the other 2 points. Perhaps more enlightening, if I take something like CP2, and so this is going to be an elliptic curve, possibly singular, and then the fiber here will be an elliptic curve, possibly punctured. Okay. So the remarkable thing I wanted to point out is now we have actually a pair of functors that kind of help structure this and relate basically mirror symmetry for Calabi-Yaus and Fanos and things. So the main ones I want to tell you about is there's a pair of functors called cap and cup that go to the Fukaya category of the fiber. So what are these two functors? So cup is actually very easy to draw. Cup, I start from, in the regular fiber, I have some little Lagrangian, let's call it little L. I put that fiber here, L. So L lives over this fiber, for example. And what I do is I transport it, I kind of spread that Lagrangian in the fiber over a U-shaped arc that goes around all the critical values. This cup of L will project to this U-shaped arc. And in this fiber, it looks like L. And of course, in that fiber, it looks like the image of L under the monodromy around everybody. It's not really in this end, it's actually, because I'm going clockwise, I will say the inverse image of L under the monodromy. Okay, so that's cap. Cap, well, I have a Lagrangian which has ends that are like fibered over some arcs, which means over here, I see Lagrangians in those fibers. If I have only one end, I just map my Lagrangian in the total space, L, to what's over here is going to be cap L. If I have several ends, what I do is I build a chain complex out of the various ends and some counts of holomorphic disks. Maybe I shouldn't tell you more to get to the end of something. So these functors are adjoint functors to each other. And the reason for that is if I look at hom in the Fukaya category of one value between cup little l and big L. So I have this U-shaped blue thing, and I have one of the others here. That's by definition inside because the U shape goes around everybody. To take their homs, I push the U shape up. And then, of course, I will see intersections in any fibers in the ends of big L. And that's exactly going to be the intersection within the fiber between little L and capital L. Big L. And these adjoint functors participate in a couple of exact triangles. So this is called a spherical adjunction. Which means there's two exact triangles of functors which I will just tell you about one. So of functors, so one is on the Fukaya category of the fiber. And best way to understand it is what happens when I do cap cup. So cap cup of a Lagrangian in the fiber means I take my Lagrangian in the fiber, I transport it over this U-shaped thing, and then I ask what are the ends of that? Well, easy. One end is little l, the other end is its image under the inverse monodromy. So that means I have the image of L under the identity functor, I have the inverse monodromy, and I think I have them backwards. Sorry. It's backwards. Okay, and the claim is there's an exact triangle of functors between those, which means that the cap cup of L is always a functorially built mapping cone between the inverse of image of L under the monodromy and L. What is this connecting natural transformation? It's given by some way of counting holomorphic sections of this fibration over these kinds of U shapes with boundaries in those Lagrangians. Why do I bother with this? That's because this has a mirror interpretation. The statement is cap and cup correspond under HMS, but not symmetry, to restriction and inclusion between the coherent sheaves of D and X. So in the world of monos, there is like a nice piece of structure that if you say do mirror symmetry for CP2, and you look at what happens in the fiber at infinity, you get a consistent picture of mirror symmetry for CP2 and for, say, a cubic elliptic curve inside it, or in general for a Fano and divisor inside it. Where this becomes a lifesaver is there's a picture of this with the rules of inclusion and restriction that are reversed that holds for arbitrary hypersurfaces in toric varieties. So the claim is we have actually, so this is built on, I think this is like Horibaffa on steroids or something, but let's put Gross-Ketzer curve for that. First we'll start, and then there's Abouzaid, myself, and Ketzer curve. We have pictures of mirror symmetry where if you take any hypersurface, almost any hypersurface, but it could be general type inside V, a toric variety. Maybe quasi-projective and semi-fan or something. But anyway, so, and in fact, there's a version for complete intersections, but the diagrams of categories become more complicated. Okay, and then we can produce a Landau-Ginzburg mirror to that, but of dimension higher than that. So let's say we have a complete, just a hypersurface. Then there's a mirror, which is of dimension n+1 to this thing, in which the fiber is mirror to V. By the way, so what's the mirror to V? Mirror to a toric variety is C star to the N with a superpotential itself, which means I'm lying to you a little bit. This is what I would call a Landau-Ginzburg model in stages. There are several functions. If you want, it's a fibration whose fibers are themselves Landau-Ginzburg models. This picture of functors extends to that. And now the claim is here there's inclusion restriction between derived categories. And here we also have cap and cup functors. And by matching these two diagrams, and given known proofs of homological mirror symmetry for toric varieties, we are now able to prove homological mirror symmetry for essentially arbitrary hypersurfaces. So this is Abouzaid and myself. That was kind of meant to be the punchline. So the stunning reversal of the directions. So there's something strange going on, which is like now the ambient space became the fiber instead of the other way around. That comes from a process of stabilization, which in the world of singularity theory, if I have a space with a function, I can replace it with x times c with the function f plus y times z, what is called, sorry, c squared. Okay. These things have the same singularity theory. They have also the same Fukaya category as Landau-Ginzburg models. And this is kind of a trick that allows you to always replace something that doesn't want to be log Calabi-Yau because it might be general type by something higher dimensional log Calabi-Yau with equivalent categories attached to it. So that's kind of the reason why things end up having mirrors that are higher dimension. Anyway, I should probably stop. So I'm over time.
Okay, thank you so much.
Thank you.
Up to digest at the end.
Yes, sorry, it all ended up at the end.
But so that hypersurface could just be ordinary Calabi-Yau?
It could be, yeah. And then what I will get as mirror is something that probably will be dimension 2 more, but a Landau-Ginzburg model. But I expect, I mean, because of the way we see it in stages, it's not easy to see. But if you combine all the terms and put it as a single square potential, I think it could probably be Morse-Bot singularities along the mirror Calabi-Yau. I mean, we can see that, say, for elliptic curves, for example, if you run this algorithm on a cubic in CP2, so just a cubic elliptic curve in CP2, you produce a three-dimensional mirror, but actually that function is, the function you get on it is kind of, it has a nice stratum of critical point, which is the mirror elliptic curve. But for example, the mirror of a genus 2 curve is a three-dimensional Landau-Ginzburg model in which the critical locus looks like 3 CP1s. So there's like a bad fiber with 3 components meeting pairwise in P1s with 2 triple points. And that's kind of the best mirror we have to a genus 2 curve.
Could you explain the relation of this picture to this spectral network construction for the, for the Lagrangians, which are dual to local P2? The coherent sheaves on local P2, there are this geodesics on the mirror curve, which I guess is in the fibers somewhere.
Let's see. So local P2 is like a total space of O of -3, right? So yeah. So the mirror of that indeed will look like So there's this mirror curve, or rather, what's more correctly, the mirror is a conic bundle over C star squared.
Yeah.
With discriminant with singularities along that. So now you're saying can relate coherent sheaves. Yeah, so coherent sheaves on local P2 can be related to Lagrangians in here. And essentially, right, so this is an upgrade of mirror symmetry for P2. So mirror symmetry for P2, the mirror is C star squared, but the fiber near infinity is exactly this elliptic curve, except I draw it bigger to have more space. Okay. So the mirrors to line bundles, we know from mirror symmetry for toric varieties, are Lagrangians in C star squared, which go to infinity in the direction of that fiber. So you can think of them as really Lagrangians in C star squared with boundary on this curve. Okay, so for example, yeah, and in fact, in tropical, like if you tropicalize by the log map, the elliptic curve will look like that, and they're all sections over this. And just what you do is you start from the real positive part inside here, and then you twist in the argument directions to get over line bundles. So now every such Lagrangian in the conic bundle lifts to a Lagrangian sphere, because basically over each point here you'll have an S1, the neck of your conic, and it degenerates at the boundary. And those together form an S3 out of the 2 disks. And so now the statement, I guess, is you've upgraded coherent sheaves on. Yeah, I'm not sure if I can fit it exactly in the framework I'm using, because it's somehow it's like, you know, it's a specific case where I don't think this is quite an anticanonical divisor or anything like that. But
I guess I was asking more generally what's the relation between local mirror symmetry for canonical models over final surfaces and this version of homological mirror symmetry, which doesn't know about this
about that construction. Yeah. So my guess is there will be reductions to that, but I haven't really tried to work it out in general. Actually, sorry, that's not true, because the pathway to this is actually through conic bundles. What you do to build this mirror here is actually you start by building exactly the conic bundle over V with singular locus along H. And then you kind of modify it by partial compactification and adding a superpotential to make it really equivalent to H in terms of having the same categories attached to it. So somehow you pass to the local Calabi-Yau or something like that, and you pass to the conic bundle and the local Calabi-Yau on the mirror, and then you kind of undo what you did by deforming them to kind of recover the space you started with. So maybe you're right that this is actually the heart of this trick to kind of go beyond the local Calabi-Yau case. Because I mean, these constructions, they end up being suspiciously similar to like Horry-Vafa mirrors with local curves and so on. Yes.
So, restricting to the Calabi-Yau case, the Horry-Vafa construction only works when you have a Landau-Ginzburg model and modular space. So, I mean, in general, that is not the case, or must not be the case, right? Does it still apply?
So the mathematicians have a construction basically based on Strominger-Yau-Zaslow's approach, where what you do is, okay, for Calabi-Yaus, what do we like to do? We think about maybe going towards some toric-like degeneration or something of your Calabi-Yau, at which point you see clearly coming out a Lagrangian torus fibration that comes from basically, just the moment map structure of the toric limit, and then you smooth that. And then you can somehow dualize that Lagrangian fibration, or more rigorously, what you can do is, if you started doing this on the symplectic side, you can build the mirror. Well, any algebraic space or analytic space is the moduli space of its own points. And so that means you look at the moduli space of point-like objects in the Fukaya category, so things that are supported on the fibers of a Lagrangian fibration. So this gives these algorithms based on Strominger-Yau-Zaslow, family Fleur theory, and so on, for building mirrors out of Lagrangian torus fibrations. And so now in a log Calabi-Yau, which has a toric degeneration, you can do exactly the same thing. Or you can do it as soon as you know how to build that space out of other spaces that are known to be amenable to SYZ. So basically, there's processes for doing that. But we don't really know how, if you give me a completely random log Calabi-Yau with no information about how it relates to other known spaces or toric geometry, then we wouldn't really know how to do that.
Any question online, Bruno? No. Oh, sorry. I need to somehow we notice hearing the sound here. Just a second. Try again. If you don't have any question, then it's fine. Okay. Well, let's start here again. Let me stop the